Good day, we are the Group 9 from ICE 3202 and today we will present our case study on the AZF Toulouse factory explosion. This presentation will examine the incident from a systems and safety perspective, focusing on the importance of maintenance practices and the role of safety instrumented systems in preventing catastrophic failures. On our next slide, system description, according to DECI and DN 2007, the AZF plant in Toulouse was a large industrial complex producing nitrogen-based fertilizers, mainly ammonium nitrate. The production chain involved neutralizing nitric acid with ammonia, followed by concentration, granulation, and fertilizer production. However, as INERIS 2002 notes, the facility handled significant volumes of hazardous chemicals, ammonia, nitric acid, and chlorinated compounds, which increased the risk of dangerous chemical interactions. For storage and vulnerabilities, warehouse contained hundreds of tons of ammonium nitrate. DECI and Jeans and Meran 2004 explained that while ammonium nitrate is stable under controlled conditions, it becomes dangerous when contaminated or exposed to heat or shock. In fact, contamination with chlorinated waste was suspected as the trigger factor in the explosion. ARIA 2013 further highlights weak segregation practices and poor hazard identifications as major safety gaps. Next slide. For the next slide, the disaster, September 21, 2001. On September 21, 2001, approximately 400 tons of ammonium nitrate detonated, killing 30 people, injuring thousands, and devastating Toulouse. ICHEM-E 2017, investigations by INERIS 2002 revealed deficiencies in safety culture, regulatory oversight, and risk prevention measures. The key lesson, as emphasized by these reports, is that even established industrial processes can fail catastrophically if safety barriers are inadequate. For the next slide, for the process flow diagram, the diagram illustrates the interconnected systems of the AZF plant. Inputs included hydrogen from electrolysis and a nitrogen and oxygen from air separation. This fed into ammonia synthesis, nitric acid production, and finally ammonium nitrate neutralization and granulation. According to ARIA 2013 and ICHEM-E 2017, both stressed that the production process itself was not the failure point. The real weakness lay in the storage safeguards, which were insufficient to prevent disaster. For the last slide, control and safety systems, the plant operated under the Seveso II directive, which required safety management systems, danger studies, and emergency plans. The last inspection was in May 2001, but DECI et al. 2004 note that the ammonium nitrate detonation scenarios were excluded from the hazard studies, while protective structures prevented domino effects in toxic gas storage. Warehouse Shed 221 lacked dedicated safety instrumented systems. During the emergency, more than 1,500 firefighters and military personnel were deployed, but ARIA 2013 reports that communication failures limited their effectiveness. For the next part, will be presented by my groupmate Irish.
Next, the engineering practice analysis. In this, it includes engineering decisions that are relevant. The AZF disaster was partly caused by some key engineering decisions. First, the plant stored a large amount of off-spec ammonium nitrate in Shed 221, which was an old warehouse built in the 1920s. It didn't have fire-resistant barriers, compartments, or any monitoring systems. Second, hazard studies and safety reports did not consider the possibility of an ammonium nitrate detonation. They only focused on fire or toxic releases, even though similar explosions happened in the past, like in Opal in 1921 and Texas City in 1947. Many decisions at the plant prioritized operational convenience and cost over safety. All of these choices made the plant more vulnerable and contributed to the explosion. Next is maintenance practices held in place. Maintenance at the AZF plant was done regularly, but it mainly focused on production equipment. The warehouse area, especially Shed 221, did not receive the same level of attention. Storage conditions were not closely monitored, so possible contamination or chemical mixing could go unnoticed. The handling of waste materials also relied mostly on workers and subcontractors. Because there was no strong preventive maintenance system for the storage area, hazardous conditions could develop without being detected. Third is proof testing and inspection being adequate. The proof testing and inspection at the AZF plant were not enough. Most inspection focused on the machines used in production, but the storage building like Shed 221 was not checked as carefully. There were also no proper monitoring systems to detect if dangerous chemicals were mixed or contaminated. Because of this, the risk inside the storage area was not noticed early, which increased the chance of a serious accident. And the last one is the safety system being independent and reliable. Safety systems at the AZF plant were mainly designed for production processes. However, the part warehouse such as Shed 221 had limited monitoring and protection systems. Because of these possible hazards in the stores, chemicals were not detected early. This shows that the safety systems were not fully reliable for all areas of the plant, especially in the storage area facility. For the next part to be presented by Bea.
In evaluating the safety instrumented systems of the AZF Toulouse plant, three key engineering aspects were analyzed: the presence of safety instrumented functions, the independence of safety systems from operational control, and the reliability of the safety architecture through redundancy and testing. First, regarding safety instrumented functions, these functions were primarily implemented in the production units of the plant. According to ICHEME, the ammonia and ammonium nitrate production processes use control loops such as pressure relief systems, temperature monitoring, and flow control to maintain stable operating conditions. These systems help prevent dangerous deviations during chemical reactions. However, reports from ARIA and INERIS indicate that the main storage warehouse, Shed 221, which contained approximately 300 to 400 tons of ammonium nitrate, did not have dedicated safety instrumented functions. There were no automated temperature sensors, contamination detection systems, or alarm systems installed in the storage area. Because of this, hazard detection relied mainly on manual observation by workers, which significantly increases the risk that unsafe conditions may develop without being detected early. The second issue is the lack of independence between safety systems and the basic process control systems. In modern process safety engineering, a safety instrumented system should be separate and independent from the operational control system, so that the safety functions remain active even if the control system fails. However, Dechi and Dien explained that in the AZF plant, safety monitoring was integrated with the same control infrastructure used for normal plant operations. This integration reduces reliability because a failure in the control system could also disable safety functions, eliminating an important protective barrier. The third factor involves redundancy, testing, and overall reliability. Effective safety systems typically use redundant sensors and backup monitoring systems to prevent single points of failure. In the AZF warehouse, investigation showed that no redundant monitoring devices were installed. In addition, proof testing and maintenance inspections were focused mostly on the production equipment rather than storage facilities. As a result, the storage area depended heavily on manual supervision instead of automated monitoring, which reduces the reliability of hazard detection. The next part is discussed by Jay.
Okay, thank you. The next part is the reliability and safety impact. It includes how engineering practices affected system safety. ARIA 2013 and ICHEME 2017 highlight that Shed 221 built in the 1920s was outdated and lacked essential safety features such as compartmentalization, fire-resistant barriers, and monitoring systems. This structural weakness made the warehouse highly vulnerable to hazardous incidents. Dechi and Dien 2007 and Ineris 2002 emphasized that hazard analyses conducted before 2001 did not consider ammonium nitrate detonation as a credible risk. Instead, they focused only on fire and toxic releases, overlooking historical disasters like Opau 1921 and Texas City 1947.
which had already demonstrated the explosive potential of ammonium nitrate. ICAM E 2017 notes that safety instrumented systems or SIS were installed in production units but not extended to warehouses. As a result, storage operations relied solely on basic controls and operator vigilance, without independent safeguards or automated monitoring. ARIA 2013 documents that poor segregation practices allowed ammonium nitrate residues to be stored in close proximity to incompatible substances such as chlorinated compounds. This unsafe arrangement increased the likelihood of chemical reactions that could destabilize the stored material. Next is the nature of failure. First is the design failure. ARIA 2013 identifies that the warehouse structure was outdated and unsafe for hazardous material storage. Shed 221 built in the 1920s had not been modernized to meet contemporary safety standards, leaving it structurally incapable of mitigating risks associated with unstable chemicals. Next is ICAM E27 points out that warehouse lack compartmentalization, fire-resistant barriers, and monitoring systems. These missing features meant that hazardous materials were stored in bulk without physical or technological safeguards, significantly increasing the likelihood of escalation in case of contamination or instability. For the maintenance failure, Dechi et al. 2004 explains that inspection routines were irregular and systematic proof testing was absent. This failure allowed potential hazards such as contamination, moisture ingress, or chemical incompatibility to remain undetected until they contributed to the disaster. Next is ICAM E 2017. Observes that maintenance practices were heavily focused on production equipment while warehouse safety was neglected. This imbalance reflected a received approach to maintenance, where storage conditions were not treated as a critical safety domain despite their inherent risks. Next is operational failures. Dechi and Dian 2007 described unsafe handling of off-spec ammonium nitrate residues. These residues were moved into storage without proper risk assessment, exposing the facility to instability. The last one is ARIA 2013 records that subcontractors responsible for waste management were inadequately trained in chemical hazards. This lack of training led to unsafe mixing of incapable materials, further increasing the risk of detonation. And the last is integration failures. ICAM E 2017 stresses that safety instrumented systems were applied to production units but not extended to warehouses. As a result, storage operations relied solely on basic process control and operator vigilance, leaving them vulnerable to human error. And the last is ARIA 2013 reveals the absence of independent safeguards, redundant monitoring, or automated alarms in warehouses. This lack of integrated safety system created critical vulnerabilities as there were no mechanism to detect or respond to instability in stored ammonium nitrate. Next part will be presented by Nico.
Thank you, Jade. Now for engineering improvements, the AZF disaster showed the importance of improving engineering systems in chemical facilities to address design flaws, poor maintenance, and weak safety systems. Storage warehouses should be modernized with compartmentalization, fire-resistant barriers, and proper segregation of ammonium nitrate from incompatible materials to reduce the risk of contamination and explosions. Facilities should also install environmental monitoring system and a dedicated safety instrumented systems to detect early signs of hazards such as moisture, contamination, or temperature changes. And according to ICAM E 2017, maintenance practices should move from received to preventive and predictive approaches, including routine inspections, safety audits, and continuous monitoring through sensor networks. Proper training and supervision of subcontractors handling hazardous materials is also essential to ensure safe operations. And finally, safety systems must be independent, redundant, and reliable. Using dedicated SIS, dual sensors, automated diagnostics, and fail-safe mechanisms help eliminate the single point of failure and strengthens overall safety in chemical storage facilities. And that's all. Thank you.